Hello, I'm Robin. My presentation is about modeling linguistic typology using probabilistic graphical models. This work is an extension of the research I did in 2013. The outline of my presentation includes 6 parts. Due to limited time, I'll skip the introduction and background. For background, I reviewed the literatures in language in study of language universals and the recent development in typological feature prediction. So I'll go to modeling directly. PGM, the probabilistic graphical model, use a graph-based representation to compactly encode a complex distribution over a high-dimensional space. The nodes correspond to the variables in the domain, and the ages correspond to direct probabilistic interactions between them. Very often, such models are interpreted as causal models, but the semantics of PGM is more complex than one-directional causal relationship. There are two big categories of PGMs. The first one is directed cyclic graph, which is also called a Bayesian network. The other type is undirected. For our purpose, we use the Bayesian network because we think typological features are of different importance in the language system. So why PGM? First, PGM has a graphical structure which provides a representation of a meta language, which we define as a collection consists of a finite set of features and a relationship between them. So in this representation, nodes represent the typological features and the ages represent the relationship between features. It encodes generalized properties of all languages in the available dataset. The second is because this model enables us to do probabilistic inference. So we assume universal properties of languages determine a probabilistic distribution of the features, and the relationship between features can be and should be quantified using probabilities. So model construction, to get these models, we learn structure and parameters from the dataset. There are 3 difficulties. The first one is a non-IID problem, which refers to the dependence between language samples due to geological or genealogical proximity. And the second one is a large quantity of missing values, which can be tackled using imputation methods. And third one is limited data, a small number of instances, which can be solved using bootstrap, like resampling techniques. So our approaches will propose 2 models, 2 hypotheses. One is flat, which assumes that there is no dependency between languages, and the univer, which assumes that there is dependency between language samples. And we compare two models to see which one performs better. The domain we choose for illustration is word order, and then we did a manual feature selection to reduce the original 56 features to 13. We'll keep some features and also remove some features. So this is an algorithm for learning the flat model. Using started with the original sample, we first used the multivariate imputation methods to fill in the missing values, and then we generated multiple sets of resamples. For each resample set, we learn structures, and we merge all these graphs. After we have this structure, we learn parameters using the original dataset, and then we get a graph and the parameters, and then again we fill in the missing values using MAP, and then just iterate the whole process until we reach the stopping criteria, which is the difference between the two steps. The structure scores between two steps should be less than certain value. To learn a uniform model, we assume languages belong to different groups along both genealogical and geological scales. Following the model averaging principle, we assume for each group we can learn a structure in the model. Then, through aggregating and averaging of graphical structures from all groups, we can identify ages that have higher probabilities. Such ages are assumed to universally present across language groups. So the next question is to how to choose the groups. So in the world's database, the languages is classified into three criteria: family, genus, and a macro area. We did the statistical summary of family and genus. So almost 80% of the groups have less than 10 languages, which is not an ideal dataset for learning our model. So macro areas is a better way for classifying languages. So here's the information of the 6 macro areas and the number of languages they have. Algorithm to learn the uniform model is as follows. So for each macro area, we'll learn a local model using the algorithm for learning the flat model. And then similar to the iterative process, we generate resamples and fuse the graphs, and then to get a final graph. So here's the 2 structures. The left is a flat, the right is a union. The edges are of different thickness, which correspond to the confidence values of the edges. Next is evaluation. So for quantitative evaluation, we need to evaluate the structure and the parameters. For structure, we can use a Bayesian score. For parameters, we use prediction accuracy. So to get this accuracy, we mask each of the features one by one and enhance the model to predict the value. The accuracy for one feature prediction for one language is defined as a number of characters predicted values divided by total number of features. And then for a data set within languages, the final accuracy of this data set is the average of all the languages. But we also developed 2 more models, COMP, which is learned using the complete data set, which the data with no missing values, and EM, which is learned from the original data set using the SEM algorithm. So for accuracy calculation, all complete instances are used as the test set. So it just so happened that the 2 graphs look similar. So COMP has the best performance in 2 metrics because we use the same dataset as a test set. And then among the other 3 models, Univ have best performance. So for qualitative evaluations, we could compare our work with previous works, but because we use different methods, it would be difficult. It will be difficult to say which ones are better. Here we did the comparison with Dom and Campbell's models. So they have 2 models, and then our probabilities is this orange line. So you can see the numbers. The numbers have some variations from their numbers, but the variations is not too big. The results will This is a big part. We started with the graph representation. So from this graph, we can study how the features interact with each other. So there is a direct inference if the two nodes are connected directly, and then there is indirect inference. We'll use an example to illustrate the indirect inference. So if OV is reserved, here we mark the first value or object precedes verb as a no, and then if we change the value of SV from an SV to VS, we see all the features under OV, the probabilities don't change, but then those under SV, they change. So this is just to say, knowing value of if we know the value of OV, then knowing values of SV doesn't help with knowing the features on the OV. So in other words, OV is more informative than SV regarding these features under OV. So we can also do conditional property queries. We can use one condition to query one condition variable and one query we can also use multiple condition variable and multiple query variables. So this is a top 10 pairwise probability queries, and then the top one is if an OV precedes a verb, then SV precedes a verb as the highest probability. Here's the example of a probability with multiple condition variables. So the two conditions are at the position in the known phrase is post position, and adjective known, adjective precedes them. So when we select those values, we can see the values that the probabilities changes accordingly. Next is MAP queries. MAP queries aims to find the most likely joint assignment to all variables simultaneously. So here we did a MAP calculation of conditioned on the value of OV. So you can see when it's OV, the most likely combination of values is such, and then when it's VO, the combination is like this. So we see ADP, NP, and then GN, genitive and non, they're symmetrical. They have symmetrical relations changes as OV. Probability of evidence calculates the probabilities of having particular values, so or value combinations. So if we calculate joint probabilities of all certain features, then we have a probability indicating likelihood of having all these feature values in a language. In other words, the likelihood of existence of such a language in terms of these features. So this is some examples we pick. In terms of the word order features, English appears to be the most typical language. Next is prediction of feature values using inference algorithms. So we use a tie as an example. We mask the 7 values. We mask the 7 values, and we use 3 models to predict the values. And then the union models predict all value correctly. And then this is another language, Hakka. For this language, all 5 values are missing from the WALS database. So we decided the true values through elicitation from the native speakers. And then we can also see the univer model have a very good performance. Prediction of macro areas. So we have six local models, and then so for example, if we pick Mandarin, we can calculate the probability of evidence, and then the Southeast Asia model gives the highest probability, which indicates that Mandarin belongs to this area. Okay, finally, conclusion. So the conclusion is we develop a unified model, generalized typological properties across geographical and genealogical language groups. So PGMs provide good solutions to existing problems. So through it has very good explanatory power to explain the language universals, so the dependence between typological features. It also has a very good predictive power to predict the missing values and then also the area information. Besides, the models also provide a new insight and perspectives. So from the graph structure, we can see more details about the inference between the features. And through the probabilistic queries, we see there's more ways to explore the typological properties of a particular domain. So ongoing in the future work, we're refining model learning algorithms, refining models for other domains, and validate the results using language examples and applications. And finally, we need to do the quantitative evaluation, compare with other works and models. But the problem is for our model, we needed to feature pre-processing, like remove some features. So this poses a difficulty. And we'll see how we'll do this. Thank you.